Hi, welcome to episode 5 of the Zero Pages. In this episode, we'll be continuing on from what we did in the previous episode, where we put a sprite on the screen, but instead of manipulating sprites, we'll be manipulating the background. Now, I know I said in the previous episode's ending that we would be going into the details of the PPU. However, after thinking about it for a while, and I realize it's a long while because if you've been waiting for this episode since the last one, it's been several months. Sorry about that. But in thinking about it for a while, I realized that I wanted to do the same thing that we did with sprites, but with the name table and updating the background. And then episode 6 will begin one of several episodes covering various detailed topics about the PPU. To get started, you'll need to download the project from GitHub, and I'll have a link to the project in GitHub in the video description below. Download the project and put it in a new folder called Hello World instead of Hello Mario. I figured that was a good title since that's what most first programs are called, and we'll be actually working on populating the background this time instead of the sprites. Once you have the project downloaded and renamed, open it up in your code editor of choice. In this case, I'm using Visual Studio Code. And then I just want to point out before we get started that in the make.bat file that we had in the Hello Mario project, originally, the --debug file option was creating a file called hello mario.debug file. That was actually a mistake. It should just be hello mario.dbg. And that's important because if you plan on using that debug file, the emulator won't open it up if it has the wrong extension. So I just wanted to point that out in case anybody was trying to use the debugging and it wasn't working for them. Okay. So before we get started making any changes to anything, we'll open the hello mario.asm file, but let's go to our command prompt, run the make.bat batch file, make sure it generates an NES file, and that when we run that in the emulator, like you see here, we're actually getting Mario appearing on the screen with the blue background like we did last time. It's always good to make sure that your starting point is something that works and works the way that you expected, so that when you make changes, if something goes wrong, you know that your starting point at least was good. Okay, so let's move down to the bottom of the file where we've defined our palette data. Now you can see here that the palette data was typed directly into the file like this. There's not much data, so I figured that was probably the easiest way to include it, rather than including it from a separate file. But with the world data, because it's a 32 by 30 grid, which means that we're going to have a lot of data that we have to import, I didn't want to clutter up the file by including all of that data here directly in the source code. We certainly could have done it that way, but given that the data itself is not so much what we're focused on, I figured it's just cleaner and easier to import the file. So we're going to import the file called world.bin by typing in .incbin or include binary world.bin. It's similar to what we did with the hello mario.char file below. Just this is the world data and not the character ROM data. I forgot to mention, if you want to download the world.bin file to follow along at home, be sure to download that from the link in the video description below as well, and place that into the folder where you've got your Hello Mario, now Hello World test project. Okay, so we've included this binary file. What does that do for us? Functionally, not a whole lot. What it's doing is it's having the assembler bring in that binary data into our .nes file when it assembles the file, but we're not actually doing anything with that. So let's change that. Let's write some code that actually pulls that data and uses it to populate the background. So let's go to the load palettes and the load sprites area of the code. In the load palettes area, if you'll recall, we're loading all the palette data into the PPU just that one time. For the sprites, we're loading the data into memory, and then it's used on every NMI to refresh the sprite data in the PPU, because we have to do that every frame, otherwise the sprites will not show up after the first frame. So let's create a label here called load world, and this is where we're going to write the code that loads the world data into the PPU. Right above that, we'll initialize the X register to 0, because like with our other loops, we're going to be using X as one of our variables for keeping track of where we are in the loop. Now, this is where things get a little complicated, and this is why I wanted to tackle sprites first instead of the backgrounds. So Our first challenge comes in the form of keeping track of how many of the tiles we've loaded on the screen. If you'll recall from before, I said that there are 32 by 30 tiles for a total of 960 that we have to load on the screen. Now, all the previous loops we've done have been counting up to a value less than the value 255, which is the most that one of the registers can keep track of because they're 8-bit registers. If the reasoning behind that is a little bit fuzzy to you, go back to the episode on number systems where I cover how number systems work, including the binary system, and hopefully that will help you understand that limitation. So, how do we deal with more than 255 elements? How do we deal with something where we need to hold a value that's larger than what the registers can actually hold? The answer is we're going to cheat. I say that somewhat tongue-in-cheek because, well, there's no cheating really. It's not some sort of special hidden instruction or 16-bit mode or something that would allow us to represent larger values in the registers. Instead, what we're going to do is instead of using just one register, we're going to use two. So instead of just having one register that can represent a value from 0 to 255, we're going to have the one register that does that like we were doing before, but we're also going to have a second register which will count how many times we've gone from 0 to 255 and back again. And if you do the math, you'll find that now we have the ability to iterate over 65,536 elements. We now have the ability to represent the value from 0 to 65,535. If you've ever looked at the maximum value a 16-bit number can hold, well, it's 65,535. And that's no coincidence. It's because we effectively are implementing our own 16-bit counter. The next challenge we face is, because we're using two of the 8-bit registers to effectively create a 16-bit register, how do we access the data that's beyond the value of 255? If you look at the way that we're loading the palette data, for example, we're using the palette data label, comma, the X register, and that works as long as that X value doesn't exceed 255. The problem is that we're definitely going to exceed that value, which means that we have no way of indexing into all of the background data, which is represented by 960 individual bytes. And because the 6502 is an 8-bit processor, it doesn't let you use the X and Y register together as a single counter. So you can't do load A, world data, comma X, comma Y, or something similar to that. That just doesn't exist. There's no instruction to handle something like that. But what if we could move the world data label itself by 256 bytes every time the X register counted 256 times? Well, that would work, right? Because we would go through the first 256 bytes, and then we'd move the world data label, and then we'd go through the next 256 bytes. But unfortunately, you can't do that with labels. They're fixed in place, and they point to one spot in memory. Thankfully, there is a way to handle this, and it's actually pretty straightforward. So let's get started on implementing that right now. The first thing we need to do is define a variable that we're going to use to hold the address of the world data as it exists on the cartridge. The reason we need to do that is because, unlike the label, if we load the address into the variable, well, variables are variable, right? You can change them. So now, once that address is loaded, we have the ability to manipulate it in any way that we want. Let's go up to the 0 page segment. And in the 0 page segment, we're going to type world : we're giving the variable a name. And then we're going to use the res directive to tell the assembler that we're reserving bytes of memory in the 0 page segment. So in this case, we need 2 because addressing on the 6502 is actually 16-bit. Once that's done, let's go back to our load world area of the code. So now that we're here, what we need to do is we need to load the address from the world data label into the new variable that we've created. Now, because the instructions in the 6502 are all 8-bit, like we were talking about before, you can't just load the address of the world data label into the world variable in one instruction. Instead, what you have to do is you have to get the first 8 bits of the world data label, the low byte, and load that into the low byte of the world variable. And then you have to get the high byte of the world data label and load that into the high byte of the world variable. So using the LDA instruction, or load A, we're going to load A with the value of the low byte by doing LDA pound less than world data. And pound less than is just a directive that CA65 supports to get the low byte of a label. From there, we're going to store the value of A into the world variable. Now, that store is just an 8-bit store, so we've only done half the job. Next, we need to do a load A of pound greater than world data, which is going to get the high byte of the world data label. Now, we're going to take that high byte and store that into world +1. The assembler is smart enough to understand that what we're telling it is to not store it in the world variable and add 1 to it or something crazy like that. We're saying store it into the address that world references, but add 1 to that address. So we're effectively populating that second byte of the variable with the high byte, and therefore we've completely set up that variable to address the world data on the cartridge now. 2 things I want to address before we move forward. The pound greater than, pound less than, and what they do. I confuse those all the time. So if you're confused by those, don't worry about it. Just try it out and you should be able to figure it out on the first attempt through the debugger, and eventually you'll remember what they do. They're certainly not the most intuitive instructions, but it just takes some time to get used to. The second part of this is, if you're not fully understanding what's going on here with the addressing and the low byte and the high byte and stuff like that, don't feel frustrated. I know that this is something that I'm going through pretty quickly, and I'm trying to explain as best as I can, but if you've never dealt with direct memory manipulation before and low-level hardware like this before, it can definitely be daunting and it can be confusing. But rewatch the section a few times. If you still don't understand, put a question in the comments below, and I'll get back to you as quickly as I can. I'm happy to help clarify anything I can right away. And maybe we'll do a follow-up to this video where I just do a Q&A based on things that were truly confusing to people after watching this. So now that we have our variable configured to point to the actual world data on the cartridge, we need to set up the PPU to be ready to receive the data. We do that in the same way that we set up the PPU to receive data for the palette, by setting the address of the location in memory on the PPU side that we want to populate with the data. Because remember, the PPU has its own RAM that it uses only for the purposes of drawing. So the area that we want to populate with this world data is called the name table. There are actually 4 of them, but I'm not going to get into the details of it because it's confusing and complicated and beyond what we need to know for the purposes of just getting something to show up on the screen right now. Just suffice it to understand that there are 4 of them that work in a complex series of ways that we'll talk about later. For the purposes of our example here, we're going to be using the name table that begins at 2000 hex. Now, this is the first name table. Not that you need to know that for this example right now, but I just wanted to point that out. It's the first name table, and that's why we're using it, because we don't have to do any crazy manipulation of anything to make it show up on screen once we populate the world data. So just like with the palette data, we're going to start by telling the PPU what address we want to manipulate. So we're going to start by loading the high byte of the 2000 hex into A by doing a load A to 0. And then we're going to store that into address 2006. Then we're going to load the low byte, which is just 0 hex, and we're going to store that into 2006. And now we've told the PPU, oh, wait, hold on a second. There's something we didn't talk about. So in the first part of this code where we load the palette up, we set the address that we want to write to in the 2006 register, and then we write the values into 2007. Everything looks great. But generally speaking, you could be doing this, a bunch of times as you're manipulating data in your game, and there's a problem. What if you write something into 2006 and then something happens and then you want to write a new value into 2006, but you've already written your first value? Well, then the first value you wrote is the first part of the address, and then the second value you wrote, thinking it's the first value, becomes the second part of the address. And then that's a problem because now you write another value to 2006, which is going to overwrite the first value in the address. Now you're going to get some sort of crazy address that doesn't work at all. Thankfully, there is a way to fix this, and it's actually pretty simple. All you have to do is read from the memory address 2002, because that's another register in the PPU. And by doing that, it resets the latch that is used to determine which byte of the address you're writing for the 2006 address. So another way to say that is that reading from 2002 will automatically reset the PPU to know that the next value you write to 2006 is the first byte of the address, and then this next value you write is the second value of the address, which is what we want. So let's go change our code. We're going to add a bit operator, which is essentially just a read, but it's a little bit faster than a load A because we don't actually care what the value is necessarily. We just want to read from that address, and then we're going to do bit 2002. Okay, finally, now that we've done that, we follow that up with our write of the value 20 into 2006 and then 00 into 2006, which is setting up the name table for us to use. And now the only other thing we need to do is similar to the load X0 that we're doing, we need to do a load Y because we're going to use Y in our loop as well. The first part of this loop is really simple. We're going to do load A, and then we're going to use the variable world in parentheses, and we're going to put a comma Y after that. We want to load a value is what we're saying here. And that value is at the world address plus Y. So if the world variable has the value 4000 in it and Y is 5, what we're saying is we want to load the value at memory address 4005 into the A register. Of course, what's at that location is our world data that we're going to use to populate the screen with a background. Once we've loaded that, we want to store that into address 2007, which is going to put it into the PPU memory for us. Then, just like with our other loops, we're going to increment Y as part of our counter, and then things get a little more complicated. If you'll recall, not that long ago in this video, I talked about how we were using 2 counters and 16-bit math and stuff like that. Well, what happened to that stuff? Where did that go? The answer is it's right here. This is where we're going to have to use both the X and the Y register as our multiple counters. The Y register is going to be used to count through the individual elements going from 0 to 255. The X register will keep track of how many times we've done that. Now, if we look at the value of 960 in hex, the value is 3C0. So what that would mean is that the X register would have to have a value of 3, and the Y register would have to have a value of C0 before we're done looping through all of the elements in the world data. Well, that's not too hard. We know how to compare numbers, right? So what we would do is we would compare first the X register against the value 3. And the reason we're using the X register as our first comparison is because it doesn't matter if the Y register has the value of C0 unless the X register has the value of 3. So there's no point in checking Y until we've confirmed that X has the value we're looking for. So first we're going to compare it against 3. And then if it's not equal, we're going to skip the comparison against the Y. So I'm using this strange thing, colon plus here after my branch not equal. What does that mean? Well, that's just a quick shorthand that lets you create labels without naming them. It can be really useful for stuff like this, and I'll show you how it works as we progress through this part of the loop. So if it's not equal, we're going to branch to colon plus, and I'll show you what that is in a moment. And if it is equal to, we'll fall past that branch if not equal. We're going to compare Y against C0. And if it's equal, then we're going to jump to a label called done loading world. because we're done loading all the data. If we're not equal, then we don't want to jump out because we're not done loading the content of the world. So we've checked our X value, we've checked our Y value if the X value is 3. Now that that's done, we need to actually create that unnamed label that I was talking about before. And we do that by just creating a colon on an empty line there like that. And that basically just says that in the code before there, if you have a branch where you do colon plus, it knows to go to the first unnamed label following that colon plus. Again, it's a neat little shorthand. It helps you write some code that's a little bit more compact without having to come up with all sorts of creative, clever names for loops. If you're not feeling comfortable using it, don't use it. It's an optional thing, and I can totally understand why that might confuse you at first. So the next thing we need to do is we want to compare y to the value 0. Why do we want to do that? Well, because if you think about the way the loop works, when you enter the loop, y is equal to 0, and we immediately increment it to 1 after storing the value into 2007. So when would y actually be 0? The answer is, after we've incremented the value of 255 by 1, the register will go from 255 to 0, which means that now we have to increment the X register to keep track of how many times we've iterated through 256 elements. So we compare y to 0, and if it's not equal, we just go back to the load world label because we want to get to the next piece of data that's at the appropriate location in memory. If it's equal to 0, then we know we've iterated through 256 elements and we need to increment X as part of our counting to ensure that we are only loading 960 bytes. So if y is not equal to 0, we're going to go back to load world because there's nothing that needs to be done. But if it is equal to 0, we want to increment X to keep track of how many elements we've iterated over. And then we need to do something else. Remember, the world variable is keeping track of where on the cartridge we're reading the world data from. And similar to the fact that we have to increment the X variable as part of our counter to ensure that we go through the data properly, we need to increment the world variable in a similar way. And the way we do that is we increment the world variable plus 1. And the reason for that is world plus 1 is the high byte that we loaded into memory. And so once we add 1 to that, it's the same thing as essentially adding 256 to the address, which gets us to our next chunk of data that we want to load into the PPU. After that, we just jump back to load world because we still have more to do. What's going to kick us out of this loop is when X is equal to 3 and Y is simultaneously equal to C0, as we talked about before. Okay, and now that all of that's done, all we need to do is create our label called done loading world that we're going to use to jump out of that loop. And then we should be able to assemble our code and run it. So let's do that. So I go to the command prompt, I run our make batch file, and I launch the ROM, and well, it looks like the background loaded, but why is everything sort of green? That's weird. Well, obviously I knew this was going to happen. I just kind of wanted to demonstrate it. The problem is that we didn't completely load the background data. I mean, the data is loaded, but there's a crucial missing piece of information that the NES needs to display backgrounds properly. So let's take a step back for a second and think about this. The way that the sprite worked is we loaded the sprite data from the char file, but then we had to also load palettes into the PPU in order to ensure that the sprite loaded with the correct colors. Because if we didn't do that, we would get Mario on screen, but with all sorts of weird colors, almost like if you painted a paint by number with the wrong or mismatched color set. One thing that I didn't mention in the sprite episode is, well, yeah, we loaded the sprite data, but how did the NES know which sprite palettes to use for our sprites? And the answer is that in the sprite data we loaded, we told the NES for this 8x8 sprite, use this palette. So that's great because that means then the sprite uses the right palette. It looks like it's got the right colors. But how does that work for the background? Because we only talked about loading individual bytes. In fact, we talked about loading 960 bytes, which is exactly the number of bytes required to populate a 32 by 30 grid. So one of the things that Nintendo did to save on space and make the NES a little bit more efficient is they didn't allow you to specify the palette for the background tiles directly. Instead, what they did was they used a system they called attributes. One thing I didn't mention previously was that the name tables are actually 1024 bytes. So if you do the math real quick, you'll notice that that means that there's 64 bytes left over after you've populated the full 960 bytes required to fill in all the 8x8 tiles. And what Nintendo did was they used those remaining 64 bytes to divide the screen up into 64 regions. And within those 64 regions, you use certain bits within each of those bytes to determine what tiles use what palettes. Now, I'm doing my best to depict this in a simplified way so that you kind of get the point. But if you feel suddenly overwhelmed with concern, frustration, confusion, don't worry, you're not alone. The attribute system in the NES is one of the most complicated and annoying things about working on the NES. And there are ways around it. There are things that you can do to make your life simpler, but let's just skip all of that for the purposes of this example, and I will show you how to populate the attribute bytes, but I won't make you sit through the tedious task of understanding exactly why those bytes work the way they do. Basically, what we're doing is we're setting one palette that will work for all the background tiles, and we're just going to blast those values into the attribute table so that it looks right for this example. In a real game, it doesn't always work that way. You might have to change which palettes are used for the background tiles, which means you have to manipulate the attribute table. And that can be very complicated and very tedious and very difficult to debug. I'm not saying this to discourage you from programming on the NES, but I am saying it so that you understand that it's a pain for everybody. Literally every NES homebrewer I've talked to has said that the attribute table is one of the most frustrating parts of working on the NES. So let's just skip it right now. So continuing on from where we were, we're still going to reset X to 0 because now we need to count from 0 to 64 because we're going to load the 64 bytes of the attribute table. We're going to create a new label called set attributes. Then we're going to load A with the value of 55. 55 is the value that we need to populate the attribute table to point to the appropriate palette that we've loaded previously into the PPU. We don't have to go into the details of why, it just works based on the way the attribute table works, and we can go into more details of that in future episodes when we cover the PPU in more detail. Then we're going to store that value into 2007 because 2007 is still storing into the name table like it was when we were loading the world data. From there, we're going to increment X, and then we're going to compare X against 64, which is 40 in hex. And if it's not equal, then we're going to go back to the set attributes label because we're not done with our loop of setting up the attributes. Okay, and then all we have to do at that point is initialize X to 0 and Y to 0 now that we're done with setting up the attributes, and then we can continue on to our load sprite code that we had before. So now we go to the command line, we run our make batch file, we get our ROM, we launch it in the emulator, and look at that. The background looks almost 100% correct. Now, if you've played Super Mario a bunch, you know that the question block doesn't look exactly right. And part of that is because it uses, I believe, a rotating palette to make it look like it's blinking. But the rest of the brick and the background floor looks correct. And that's because we've actually changed the palette that's being used for the background to use the appropriate palette. And that's it for this episode. I want to first and foremost say I'm so sorry that this took so long to get released. beyond just the delays of getting a video made and how long it takes to create and edit this video, it ran into, as I mentioned in another channel update video, the birth of my son. And having another baby that is little, as any parent knows, takes up a huge, huge amount of time, not only during the day, but also during the night. So I appreciate all of you who have been so patiently waiting and commenting on the old videos and asking when it's going to be done and asking great questions. You have no idea how much that makes me want to keep making videos. I really, really appreciate it. And I feel so good to know that these videos are helping people. As always, if you have questions, please don't hesitate to ask in the comments below. You can reach me on Twitter at Clearvis. You can reach me on Video Game Sage as Zelius, and you can email me at zelius@gmail.com. I also just want to put in a quick thanks to the patrons on patreon.com. I appreciate you all so much. I appreciate the support and how much you believe in what I'm doing, and I can't say thank you enough. Thank you so much. Take care, everybody. Have a great day, and I hope to hear from you in the comments below. Keep on programming, and like I always say, never hesitate to ask questions. I'm here to help.